In this video, we're going to talk about how one might use a calorimeter to measure directly a heat of reaction. Our learning goals include evaluating the heat exchange that's caused by a chemical reaction and to see an example of how it might be measured in a calorimeter. We're going to use a neutralization reaction to illustrate this. A neutralization reaction has the general form that looks like this. All right, now what's being neutralized here is it's an acid reacting with a base. And in this case, we've got HA, which is the acid, reacting with MOH, which is the base, to produce water and an ionic compound, Ma. Actually, this ionic compound is also called a salt. Now, we're going to assume that these are strong electrolytes, so they completely dissociate into ions. So it'll look something like this. The HA will split up into H plus and A minus. The metal hydroxide will split up into metal ions and hydroxide ions. All of this is an aqueous solution. Now, when the reaction is done, the H plus and the OH minus will combine to make water, which is in liquid form, and we'll still have the metal ions and the A minus ions in the solution. Now, one of the things you'll notice is that these things appear on both sides of this equation. So they are, in fact, spectator ions. So if we want to deal with just the net ionic equation in this case, it's simply going to be H plus OH minus goes to water. And this is the classic form of an acid-base neutralization reaction. So now we want to measure the enthalpy of this particular reaction. So here it is again. Now, one of the first things you should notice is that we're basically forming a new bond. We've got two ions together. They're going to come together to form a new covalent bond between hydrogen and oxygen. So whenever a new bond is formed, that means energy is released. So we should expect this to be an exothermic process. Now we're going to test this by mixing two solutions, one that contains 0.08 moles of sodium hydroxide and another that contains 0.08 moles of nitric acid. And we're going to find that the temperature change in a calorimeter that contains 100 mils of water is going to be plus 10.3 Kelvin. So already we have a clue that it is indeed an exothermic process because the temperature of the calorimeter went up. So in other words, the system released heat to the calorimeter. So now, as an activity, I'd like for you to use this information to evaluate the enthalpy change for the neutralization reaction. So you may pause the video and try that out. Hopefully you've had a chance to do that now. So the answer is going to be the following. The heat capacity of the calorimeter is going to be its total water, 100 mils. Now we need to convert that to grams. Water has a density of 1 gram per mil, and it has a specific heat capacity of 4.184, so when we multiply all of this together, we'll find that the heat capacity of the calorimeter is going to be 418.4 joules per Kelvin. Once we have that, we can now calculate the enthalpy change for the reaction. Now it's going to be the negative of the enthalpy change of the calorimeter, so the enthalpy change of the reaction is going to be negative times the heat capacity of the calorimeter times its temperature change, which was 10.3 Kelvin. So when we multiply all those together, we find that the overall enthalpy change for the reaction is negative 4,320 joules. Now, this is very specific to having mixed 0.08 moles of each of the acid and the base together. But what might be more useful is if we were able to get a heat of reaction that applies to a full mole of stuff being reacted. That way it's a standard that then can be scaled to whatever amount we might have. So delta H is an extensive property. It scales with the amount of material. So this is the whole point I'm making here. So we know that 0.08 moles of starting material, reactants, produces a heat change, an enthalpy change of negative 4,320. If I had twice as many moles, because it's an extensive property, it would create twice the heat, or negative 8,640. So what we can do is we can set up a proportion of relating this enthalpy change to the number of moles. And it looks something like this. So if the enthalpy change of the reaction divided by the number of moles is going to be a constant. As the number of moles increases, the enthalpy change of the reaction would increase in a proportionate manner. So this ratio must be constant. So we know that negative 4,320 joules is the amount that 0.08 moles generates. What we want to find is what is the amount of energy or amount of heat that is generated by 1 mole. So we would solve this equation for x. And when we do that, we would find that x is equal to negative 54,000 joules. So that tells us then that the molar heat of neutralization, in this case delta H, is going to be negative 54 kilojoules per mole. And now I've substituted kilojoules for joules, so I'm not writing out a big old number like 54,000. So I hope this made sense, and it's something that you'll be able to apply to other reactions as well.